Welcome everyone to today's problem solving session of the course Microwave Engineering. Today we are having our session 9. Uh, as you know, this has been postponed due to some unforeseen circumstances. So, without any delay, I would like to take the session on. So the content of week 9 for this course was on microwave tubes, on which we are going to have our discussion today. So initially the discussions in the video lectures have started with the limitations of conventional tubes at microwave frequency range. So why we are going for the microwave tubes as such. And then we have come across the different types of microwave tubes. Say it is whether amplifier or oscillator. So we started out by seeing the klystron amplifier, then the reflex klystron or magnetron oscillators, and then also the traveling wave tube or TWT amplifier. So as you know, this is an amplifier. Again, this is oscillator, and again this is an amplifier. So basically we have looked at different microwave tubes which can be used as an amplifier or an oscillator. So first of all, let's start with the very first question. Why the conventional vacuum tubes fail at high frequencies? So just to understand how much you could gather, can you please comment on this question? Can you please give your comments on this question? What do you think, why the vacuum tubes fail at high frequencies? Or why we have to go for the microwave tubes? Yeah, so as you said rightly, wavelength is small, so maybe you are referring to the high frequency, right? So whenever you have a high frequency signal, as you know, the time period of that signal is small. And the one of the very important fact to understand here is, uh, in case of vacuum tubes, the lead inductance and also the interelectrode capacitance. Okay. So as the frequency increases, these become dominant. Okay. So I will just quickly write these points. These are really very important. The lead inductance and the interelectrode capacitance. So these two become dominant at high frequencies. So the real part of the input impedance is becoming low, which will short circuit the source and which will reduce the power output from the vacuum tubes. So that is one of the reasons why we not use the vacuum tubes. Okay, now coming to the second reason. So to talk about second reason is something which you have mentioned, like the frequency is high. So whenever the frequency is high, the time period is small. Okay, the time period of the signal is small. So if you look at the transit time, say this is cathode from where the electrons will start moving, and this is like anode or grid or whatever it may be. So there is a transit time, that is a time taken by the electron to move from one electrode to the other. Okay. So that transit time, say if I denote it by tau or something like that. So in this case, the time period of the signal is very, very small compared to the transit time. So you imagine the time taken for the electron to move from one electrode to the other electrode is large compared to the time period of the signal. So in this itself, you will have multiple time periods and there will be multiple oscillations in the electrode. So the polarity of this electrodes will keep oscillating and the electrons will keep oscillating back and forth, which will eventually reduce the tube efficiency. Okay, which will affect the tube efficiency. So this is one fact. This is another reason due to which the vacuum tubes are not good at high frequency. And I have one more reason to point out, that is the gain bandwidth product. Okay. So in any amplifier, like in the vacuum tubes kind conventional amplifiers, there is, if you go for a maximum gain, then in that case the bandwidth is limited. Okay, so this all these limitations have been overcome by the microwave tubes. Okay, and we will see how the microwave tubes are, how good they are. Okay, now a quick question, it's a general question to ask you. As I told about a few names of the amplifiers and oscillators in the beginning of the session, say I told you about the oscillators, let me look at these specifically. So these are reflex klystron and magnetron oscillator. So my question is, do you know what is the type of oscillator used in a microwave oven? So the commercial microwave oven which we use in our home as a home appliance is, which is the type of oscillator? Yes, right. You are right. It's a magnetron. And an associated question to that, do you know what is the frequency of, what is the frequency? So you know that it's a oscillator, it will generate a frequency, right? It generates a microwave frequency. Do you know what is the frequency range, or what is the frequency which it generates in case of a commercial microwave oven? Yes, right. It is in the range of microwave oven, but any clues about the number?
From 9 to 12 gigahertz, no? The
Uh,
frequency.
Sorry, that's not the right answer. So the right answer is the 2.4 gigahertz. Okay. If you remember, this is a quite bit known number to us. Even our Wi-Fi systems work at this 2.45 gigahertz. So even the microwave ovens will generate this particular frequency, that is 2.4 gigahertz. So this is just an information to give you an just a
Madam, 2.4 is for ISM band applications, no, madam.
yes, but even the ovens will generate the same frequency. I mean, this is an oscillator, right? So this oscillator is generating a frequency, a high frequency signal. So it's at the range of 2.4 gigahertz. You can look at the specifications of a microwave oven. You will definitely see that it's a magnetron oscillator and it generates 2.4 gigahertz. Okay. I suggest you please go through any of the specifications, or you can even search in internet. Okay. Okay, now let's move to some of the questions. So before moving on, I hope you know you have the understanding of the tube cavity klystron. So this will be the very first discussion. A few questions will be based on tube cavity klystron. So as you know, the structure of the amplifier. So this is your cathode from where the electrons are generated. This is the this is the anode, which is having a positive potential which will attract the electrons, and then it reaches the, so this passes through the this and reaches the first cavity, which is called as buncher cavity. And you see this is an RF input here. In the buncher cavity it is being applied, and in the buncher cavity there is a modulation happening here. So that's called as velocity modulation. So based on the signal, say if the RF signal is having a positive cycle, the electrons will have a increased velocity. I mean, electrons will speed up, and for a negative cycle, electrons will slow down. And then in the zero crossing areas, electrons will have a same speed. Okay, that is called as velocity modulation. Okay, then the velocity modulation will result in bunching of the electrons, and then it moves towards the catcher cavity, wherein the RF output is being taken. Okay, so basically what happens, the amplified RF signal is being taken out from the catcher cavity. So here what happens, the working principle and all, you know, the kinetic energy and how that kinetic energy is being converted to the amplification. I mean, the energy is being transferred to amplify the signal, and the slow down electrons are being collected by this collector. So I have just given a quick review or recap of what is a tube cavity klystron. There are a lot of things which I have not told. Let us go through some of the questions so that we will see what we understood. So the very first question, microwave tubes are grouped into two categories depending on the type of. So these two categories, let me just elaborate. One is the O type tubes and the other is the M type tubes. Okay. Now I would like to give a little more explanation on this. So this O type tubes are nothing but which is having a linear electron beam field interaction, and in M type there is a crossed field interaction. So can you tell what is the right option here? How we are dividing this into two categories? It's based on what? Is it based on the amplification method, electron beam in field interaction, power gain achieved, construction methods? You can comment A, B, C, D among this, which is the. So if you look at this O type and M type, I told you this is a crossed field. So the electron beam and field interaction. So suppose if the focusing field is perpendicular to the accelerating electric field, then we call it as a crossed field. So basically it is being divided into two categories based on the electron beam field interaction. Okay. I hope you understood this. Okay, right answer. Okay, now going to the next question, because these are just conceptual questions, I am just moving through. So if you have any doubts, you can ask. Okay, so the next question is, the klystron tube used in a klystron amplifier is what type of beam amplifier? Is it a linear beam? Is it a crossed field? Is it a parallel field? No, none of them mentioned. Yes, right answer. It is a linear beam type of amplifier. Okay. Or we can say it as O-type amplifier. Okay. Now the question comes about crossed field tubes. Okay. In crossed field tubes, electron beam traverses the length of the tube and is parallel to the electric field. Is it true or false? Is it the electron beam the traversing is parallel to the electric field? So the beam, we can say the beam travel or beam what creates the focusing field. We can call it as a focusing field. That is what which is being created by the electron beam traversing through the tube. So is the focusing field being parallel to the electric field in case of a crossed field tube? True or false? What do you think? Type in the chat whether you think it is a true or false. So, a crossed field tube, as I mentioned in the beginning, it's the M type tube wherein the electron beam field interaction is basically perpendicular. Okay, so the focusing field is perpendicular to the accelerating electric field. So, this is a false statement. I hope this is clear now. Okay, so now moving on to the next question. In which is a single cavity klystron tube that operates as an oscillator by using reflector electrode after the cavity. Which is the single cavity klystron which will act as an oscillator having a reflector electrode after the cavity. Yes, right answer. It's a reflex klystron. So if you look at, I have a figure of the reflex klystron over here. So this is basically an oscillator. So you see this is the cathode which will generate the electrodes, and you have an anode which will accelerate the electron beam, and then you have this one cavity, that is a single cavity. Okay. Unlike the two cavity klystron amplifier, here you have only single cavity, and you see there is a Vs which is mentioned here. So this is some feeble signal which is inside the cavity, which is getting amplified with the help of a feedback. Okay, what is giving you the feedback is your repeller electrode or a reflector electrode. So because this has a potential, see, this is a negative potential. So the electrons will be obviously repelled away from the this particular electrode, and then again moves towards the cavity. So this cavity area. So this multiple times of movement will gives a feedback, which in turn creates a oscillation. So basically a high voltage oscillation. So that is being collected at here RF as an RF output. So this is the rough structure of our flex klystron. Okay, now let's move on to the next question. The major disadvantage of a klystron amplifier. Okay, so let me again quickly look at what amplifiers we have. We have klystron and TWT. So what is the disadvantage of klystron, or what is the benefit of TWT? It could be same. The question is same. What is the major disadvantage of the klystron amplifier? Is it about the gain? Is it about the bandwidth? Is it about the power? Is it about the design complexity? What is the major disadvantage? Yes, right answer. That's the low bandwidth. And that bandwidth issue is being overcome in the TWT amplifier. Okay. Now, coming to the next question, magnetrons are microwave devices that offer very high efficiency, about 80%. Is it true or false? So as I told before, magnetrons are oscillators used in microwave ovens. So you can guess a little bit. Is it a true statement? So if you look at the specifications of what kind of powers it gives, any idea what is the order of power a magnetron or the microwave oven is generating? That's generally in the of the order of kilowatts. Okay. So what do you think? Is the magnetrons efficient or not? So let me tell you, this is true. Magnetrons are oscillators which produces very high power output with very good efficiency, and the powers are generated is of the order of kilowatts. Okay. Now going to the next question, klystron amplifiers have high noise output as compared to the closed field amplifier. So the question is about the noise. So is the klystron amplifier noisy, or the magnetron, I mean the cross field amplifiers noisy? So we have mentioned that klystron amplifiers have low bandwidth. Okay. But TWT amplifiers are better, or cross field amplifiers are better in that. But how about the noise output? Okay, to answer this, so the noisy, if you look at the noisy noise output in case of klystron and in case of a cross field amplifier, In case of cross-field amplifier, the bandwidth is good, but the noise output is very large. So basically, this is a kind of noisy, but in fact, klystron are comparatively less noisy. So this is a false statement. So now next question is a very simple question. Please do answer. In a two-cavity klystron, okay, the electrons injected from the cathode arrive at the first cavity with uniform velocity. Okay, true. That's a true statement. So, as you know, in a two-cavity klystron, initially when it reaches the first cavity, every electron is in the same with the same velocity. But once it leaves the buncher cavity, what happens? This velocity modulation happens here. Velocity modulation. So, based on the cycle of the RF signal, there will be electrons which are accelerated and also decelerated, which will eventually result in bunching of electrons. Okay. Now I have a few more questions like this, MCQs. Both axial magnetic field and radial electric fields are used in the following vacuum tubes. Axial magnetic field and radial electric field. So, I would like to show you a schematic in this case. You can, if you could remember something, you can say this. So, in which tube you have radial electric field and axial magnetic field? Is it a magnetron? Is it a reflex klystron? Is it a klystron? Is it a TWT? Where you have the radial electric field and axial magnetic field, in which of the tube? Any guesses? Maybe you will understand when I show you this figure. As you see here,
Magnetron.
yeah, this
Magnetron.
is a
Cylindrical
magnetron.
magnetron.
So remember, this has a radial electric field. Okay. So as you know, this is anode and cathode. So the two electrodes are like a what do you call, concentric circle kind. And you have the cylindrical cavity. So basically, this has a radial electric field and axial magnetic field. Okay. Okay. Now the next question, transit time can be reduced in the microwave tubes. Okay. If the electrodes are brought closer together, if high anode current is used, if multiple or coaxial leads are used. So you know, I hope you know what is the transit time. As I told in the beginning, if you have two electrodes, say cathode and grid or anode, whatever it is. So the time taken by the electron to move from the one electrode to the other is being called as the transit time. So is there a possibility in reducing the transit time by any of these methods? Very simple. Just think logically. Yes, right answer. If the electrodes are just closer, imagine if these are closer, definitely the transit time is going to reduce. Okay. Okay. Now comes a few question on. Okay, one question is on reflex klystron. We have already told. So this question is about the modes in a reflex klystron. What about the modes? Is it the modes are like giving the same frequency but a different transit time? Is it resulting from excessive transit time across the resonator gap? Are they caused by spurious frequency modulation, or are they just for theoretical considerations? What do you mean by the modes in a reflex klystron? So the right answer is yes, it gives the same frequency but different transit time. Okay. Okay, again, I have a question. I think we have discussed the concept, but I would suggest you to answer this. Vacuum tubes fail at microwave frequencies because what is the reason? Is it because the noise figure is increased? Is it because the shunt capacitive reactance becomes too large? Is it becoming the transit time too short? Series inductive reactance too small? So, in the beginning of the session today, I have mentioned three reasons why. Okay, let me take your answer. Transit time. So, you are saying that transit time is too short. So, let me tell you, I told you at high frequency, what happens? The time period of the wave is small. Okay, time period is much, much smaller than the transit time. So, basically, transit time is large. Transit time is large compared to the time period of the signal. So this cannot be the option. Now the next is think about the very first reason, the lead inductance and the inter-electrode capacitance. So that is something which is the B option and the D option. So basically the shunt capacitive reactance is nothing but the inter-electrode capacitance. Okay. Definitely that is going to increase or large. Uh, it will be very large at high frequency. Okay. And also if this last option, it is not small, definitely the lead inductance is going to be increased with the increase in frequency. Okay. So the right option here for this question is option B. Hope this is clear. Okay. Hmm. Okay, now comes this question. Main advantage of TWT over a multi-cavity klystron. What is the main advantage? I think we have discussed this in a different way. I think maybe you will be able to answer this. What was the disadvantage of uh, cavity? Yes, right. Greater bandwidth. TWT has a greater bandwidth compared to a two cavity klystron amplifier. Okay, now we have a question about the TWT. So let me just quickly show you the structure of a TWT. You know that it's a slow wave structure which is like a helix. Okay, and here you have the cathode. See, here you have the cathode and here you have the anode which will accelerate. So this will generate the electrons. This will accelerate the electrons. And you see the RF input is being applied onto one side of the coil, the helix coil. Okay. And this electron beam is going to pass through this. Okay. So that is the closed field. You see the electron beams are going to pass like this axially, and this will have a field. The magnetic field is magnetic focusing structure is there, and then this slow wave structure or the helix will make sure that the velocity, the electrons are slowed down. Okay, and finally you take out the RF output here, and this is the collector which will collect the electrons which are slowed down. Again, this concept of amplification is same. As you know, the energy which is being converted to the kinetic energy gained is being converted to the RF output amplification. So let us go to the question here about the TWT. So the question is, okay, what is the purpose of the helix structure? Is it to make sure the bandwidth is large? Is it to minimize the noise figure? Is it to minimize the RF field's axial velocity? Mm. So you are saying the option A, that's not the right option. So let me just go to this figure once again. So here you have a RF field, okay? RF field which is being applied to this helix structure. Okay, because this is a helical structure, what happens is the axial velocity. Okay, RF field's axial velocity. Don't you think that will reduce? So the RF field is going through the helical structure, which will eventually reduce its axial velocity. Okay, so that is the purpose. So that is why we call it as a slow wave structure. Helical structure has an importance. So this that makes the electron beam slow down. So this what it happens is the RF field is being applied here. Okay, there is an RF input here. If it would have been a straight structure, the axial velocity is much larger. Because it is going in a helical structure, definitely its axial velocity is being slowed down or reduced. Okay, I hope this is clear. Okay, now coming to the next question. So although we haven't noticed this attenuator in a TWT, there is a attenuator. Any guesses what is that attenuator? What is the purpose of an attenuator in a traveling wave tube? It is not mentioned in the structure here, but there is an attenuator in case of TWT. Any guesses why that? What is the purpose of an attenuator? So it is to prevent the oscillation. Okay. So the purpose of attenuator is to prevent the oscillation. So basically the purpose of TWT, as you know, it's the amplification. So we need to have a amplified signal at the output side of the helix structure. So the attenuator will ensure that it will prevent the oscillations. Now coming to the next question. Oscillating frequencies of different modes of magnetron are not same and but quite close to each other, which will result in what? Focusing, attenuation, improving bunching, mode jumping. So there are multiple modes, say this modes like 1, 2, 3, etc. So these multiple modes have frequencies, the oscillating frequencies, which are not exactly same but very close to each other. So which will result in, any guesses? So this will result in mode jumping. Okay, because the frequencies say F1, F2 are very close to quite close to each other, it can happen such that the mode 1 becomes mode 2 or mode 2 becomes mode 3. Okay, so that is one of the things with the magnetron oscillator. Now, this is just a, if you could understood about the TWT slow wave structure, you see which structure cannot be used as a slow wave structure. These are the options like coupled cavity, helix, ring bar, periodic, permanent magnet. Definitely helix is not the answer, because helix will definitely be the slow wave structure. What could not be a slow wave structure? So slow wave structure, so if you remember, you have this TWT. Here you have a magnet, which is a magnet focusing structure. So this magnet is providing a field here. So the magnetic field is provided by the magnet there. So the helix is giving the helix is basically slowing down the electron. So Helix is actually providing, helix is like, so this has a field. So this has a field and this is giving accelerating field, and the other is the, or slow down field, and the other is the magnetic field, which is a focusing field. We can call it as a focusing field. So these two are present in a TWT. So which structure could not be? So if you look at this periodic permanent magnet, that alone cannot make it as a slow wave structure. Okay, for a structure to be slow wave, somehow it has to slow down the RF field's axial velocity. Okay, only those kind of structures can be called as a slow wave structure. Okay, now the next question. The phase velocity of RF field's axial component in the TWT slow wave structure is. So I told about the RF field's axial velocity. Yes. Now tell me if that is equal to the velocity of electrons. Is it less than the velocity of electrons? Is it greater than the velocity of electrons? Is it equal to light, velocity of light in vacuum? So remember the word slow wave structure. So the RF field's axial velocity is being minimized or slowed down. So the phase velocity will be, any guesses? This is about the phase velocity. Phase velocity will be less than the velocity of electrons. Right answer. Now this question, you need to think a little bit. In the following microwave tubes, RF energy. So remember, the question is about RF energy. So we can imagine what is that. You can just refresh your concept of phase velocity and group velocity. So phase velocity is one parameter, and the group velocity is something uh, uh, which will say about the what you call the energy traveling, or the velocity at which the energy is being propagated. You can just imagine that thing. Okay, so the question is, in which of the tubes, okay, we are given with a few tubes, magnetron, TWT, CFA. So CFA is nothing but closed field amplifier, and the klystron. So in which among these the electrons are moving at the same speed? Okay, so RF energy, the question is about RF energy. RF energy is having the same speed as that of the electrons that is moving from the cathode to the collector. So initially we had the klystron. If you remember, there was velocity modulation and there was bunching of electrons. Okay, now if you remember, the RF energy travel, so the RF energy is being propagated and the electron speed, so that is not same there. Now if you remember about the TWT, actual RF energy, I told about phase velocity. So phase velocity is something which will make the uh, basically based on the axial structure. Okay, but the energy is something which is the, what you call, the kind of a group velocity, the propagation along the propagation direction. So the electrons speed, the speed at which the electrons move is same as RF energy travel speed, in case, only in case of a TWT amplifier. Whereas that is different, because if you look at the klystron, you have velocity modulation. So different electrons will travel at different speeds. Okay, then we can't say that the energy travel is same as the velocity of the electrons. Okay, that is why the klystron is not the right answer. So the right answer is TWT. Okay, now going to the next question. Which one of the following can be used for amplification of the microwave energy? Very simple question. Which among these options is used as an amplifier? Which among these is as an amplifier?
Madam, magnetron is accelerator.
Magnetron is oscillator.
Reflex crystal also accelerator.
Yes,
Both are, I think, TWT.
TWT. Gun diode, if you remember in the last week's content, we have looked at gun diode and oscillators. Gun diode oscillator. So this is also an oscillator. So the only option here is TWT.
Okay, madam.
Okay. So we will not discuss this. Now we will move to some numericals. Okay. Before I move to specific numericals, I would like to just consolidate a few things like say you have electron velocity in case of this two cavity klystron amplifier. So the electron velocity leaving the cathode, okay, it is V naught is equal to 0.593 into 10 power 6 square root of V naught. Okay. So please understand this V naught is the DC voltage applied. Okay. If you remember, in a klystron amplifier, you apply a DC voltage. Okay. Based on that DC voltage, you will have this velocity of electrons released from the cathode. Okay. So this is very important. Please make a note of this. Then the next is the gap transit angle. Okay. So we know that there is a gap between the gap spacing here in case of the the klystron amplifier. So the gap transit angle is given by omega d by V naught. Okay, omega is the angular frequency, d is the gap spacing. Okay, and then V naught is the uh, velocity of electron velocity. Okay, so that is your gap transit angle.
Madam,
Huh.
madam, that gap transit angle we are putting V naught. This
Gap.
V naught is DC voltage or this total V naught, madam? Electron velocity.
Oh, sorry. Don't confuse. This one is capital V naught. Okay. Capital V underscore naught is the DC voltage. And this one is small V naught. Okay. Small v underscore naught. So this is electron velocity. This is DC voltage. So this is electron velocity. Is it
Okay,
okay?
madam.
Okay.
Thank you, madam.
Okay. Then, so I hope you know what is the gap spacing. So gap spacing is something based on the cavity. So in each cavity there is a small space. So that spacing is called as the gap spacing. So D is gap spacing. And omega is the angular frequency. So if you are given with the F, you can make omega by 2 pi. Omega will be 2 pi F. Okay, now next point is beam coupling coefficient. Okay. Beam coupling coefficient.
Madam,
Yes.
madam, gap between two cavity and spacing between two cavities L and D, no, madam. L is space, no.
L is the length between the two cavities. D is in a single cavity, that spacing. What is the spacing there? I will show you a.
Yes, ma'am. Diagram is madam. Once.
Okay. So this you have. Have you noticed this is the buncher cavity? This is the catcher cavity.
Okay,
The
madam.
distance between these two cavities is L. Okay. And this
Okay,
gap
okay,
is
madam.
there, no? This is called as D. So this is the cavity gap spacing. It is there in both the cases, both buncher cavity and catcher cavity. This is called as D. Okay.
Okay, thank you, madam.
Now, okay. Now we are talking about the beam coupling coefficient. That means how well the beam is being coupled with the field. So sine theta g by 2 divided by theta g by 2. So these are some of the takeaway equations. You can note it down and use it for solving the numericals. Next is DC transit angle. Okay, wait. Let me complete this one. Okay. From the beam coupling coefficient, you can calculate velocity modulation depth. So I told you about the velocity modulation happening in the buncher cavity. So whenever there is a modulation associated with, we can say modulation depth, like how we tell about analog communication. There also we talk about modulation index. Similar to that, we have the modulation depth here. So this is also modulation index only. So that modulation depth M is nothing but beta I, that is the beam coupling coefficient, multiplied by V1 divided by V0. Now this V0 is the DC voltage and this V1 is the AC voltage. So AC voltage in the sense the signal, the RF signal which is being input there. So we, in case of an amplifier, you give an RF input which is an AC. So that AC voltage will have a amplifier will have an amplitude. So V1 is the amplitude of that AC voltage and V0 is the DC voltage which is being applied to the electrode. Then beta I is the beam coupling coefficient which we can find out with this equation. Okay, so the velocity modulation depth can be calculated based on this. Okay, now I think we will move to solving one question. Okay, so the question is about, as I told, about a two cavity klystron. DC voltage, that is V0. Let me denote everything. V0 is 625. Gap spacing, that is D. It is 1 millimeter. Amplitude of the AC voltage, that is V1, which is 60 volt. The klystron is operating, that is F is 2.4 gigahertz. Okay. Now the question is, what is the depth of velocity modulation? So what is the equation? M is equal to beta I into V1 by V0. We already know what is V1 and V0. But we have to find what is beta I. For beta I, what is required? Sine theta g by 2 by theta g by 2. But we need to find theta g. What is theta g? Theta g is omega d by V0. V0 is not the DC. This V0 is the electron velocity. So that electron velocity can be calculated from 0.593 into 10 power 6 root of capital V0. This is the DC voltage. So 0.593 into 10 power 6 into square root of 625. That is your DC voltage, which will give me the electron velocity. Then go back and substitute here. Can you quickly calculate and tell the values for theta, V naught? Yes, that is the right answer. V naught is 14.825 into 10 power 6 meter per second. So this is the electron velocity leaving the cathode. Now, what is theta g? The gap transit angle. How do we find that? 2 pi f. F is 2.4 into 10 power 9 into gap spacing is 1 millimeter. Make it 10 power minus 3 by V naught is 14.825 into 10 power 6. So answers for theta g. So that will be in radian. Please remember theta g answer will be in radian. Can you quickly calculate and get the answer for theta g? Yes, that is 1.017. Now, please substitute theta g in this equation for beta I. Remember, in radian. So this answer is in radian. Yes, that will be 0.957. Okay. Now, substitute in and find out modulation depth. 0.957 into 60 divided by 625. So what is the right option here? So percentage, in terms of percentage. In terms of percentage. So if you get 0.092, multiply it by 100. So it will become 9.2%. Okay. So the right option is option C. So I hope this is clear. We'll move on to the next question. In a two-cavity klystron, the spacing between the two cavities is 4 centimeters. So here it is L. L is equal to 4 centimeter. And the gap spacing D is 1 millimeter. The DC transit angle between the two cavities. So you have two cavities. Say first cavity is buncher cavity and the second cavity is catcher cavity. So the transit angle between these two is 40 radian. So the transit angle theta naught is 40 radian. And it's operating at 2 gigahertz. Depth of modulation, that is M, 10%. What will be the modulation index in linear? How we can write? M is equal to 0.1. So now the question is maximum velocity of the electron. What will be maximum velocity of the electron? So whenever this velocity modulation happens, I hope you remember, during the positive cycle of RF signal, the electrons will be accelerated. During the negative cycle of the RF signal, electrons will be decelerated. Okay, so it's moving slower. And in this zero crossing, there is no change in velocity. So finally, the electrons from the three different points will have a bunching. Okay, so as I told, there is three conditions. One is the same velocity, other is maximum velocity which is happening in the positive cycle, and the other is the minimum velocity which happens at the negative cycle. So V naught max is something about the positive cycle. In positive cycle, what is the maximum velocity of electrons? Okay. To answer that question, we should know what is the modulation index and what is the velocity of electrons. Okay. So how to take it? So let me start from here. As you know, the distance between the two cavities is L. Now, if you think about the transit angle between the two cavities, what is this theta naught? Omega t. Omega t. So theta is omega t, right? Omega is 2 pi f and t is nothing but the time. Okay, how do we find that time? Omega into length. How much is the length by what is the velocity of that? Velocity at which it is moving. So L by V naught will give me the time. Okay. So this is the DC transit angle between the cavities. Remember. Okay. DC transit angle between the cavities. We are taking the length of the cavity by velocity of electron. That gives me the, the time. And multiply it by omega, you will get the transit angle. Okay. Now, we know this transit angle theta naught. It's given in the question. We also know the angular frequency. We also know the length of this. But we can find out V naught. So 40 radian is equal to omega is 2 pi into 2 gigahertz into L is 4 centimeter, 4 into 10 power minus 2 by V naught you can find. So can you evaluate V naught from here? So this is, remember, this is not the maximum velocity. We are evaluating V naught. V naught is nothing but the electron velocity leaving the cathode. Can you quickly calculate the V naught and let me know? Yes. So the answer will be 1.25 into 10 power 7 meter per second. Now, how do we find V naught max? Remember, in case of modulation, how we used to do? V naught max will be V naught into 1 plus M by 2. Similarly, what will be V naught minimum? V naught minimum will be V naught into 1 minus M by 2. Okay, so we are interested only in V naught max, so we are not focusing on this one right now. So this will be just substitute for M as 0.1 and find out V naught max. So you can let me know which is the right option here. So the option is first 1.32 into 10 power 7 meter per second. Now there is a question on, so I hope this is clear. If there are any doubts, please ask. Okay, then we'll move to a question on magnetron. So the question on magnetron, as you see, so this is cathode and this is anode. So you can see that the radius, this is A and this is B. Okay, and from the figure it is clear that A is less than B. So the cathode radius is A, which is 5 centimeter, and anode radius is B, which is 10 centimeter, and the E by M, that is charge to mass ratio of the electron. Okay, E by M is 1.76 into 10 power 11 coulombs per kilogram. If the anode voltage is 36 kilovolt, so there is an anode voltage. Generally, we denote anode voltage or the DC voltage by V naught, okay, 36 kilovolt. What is the magnitude of Hull cutoff magnetic flux density? So, the equation for Hull cutoff magnetic flux density is 8 into V naught M by E the whole raised to half by B into 1 minus A square by B square. A and B you know, V naught you know, E by M is also known. So it's just a substitution. You can find out the magnitude of the Hull cutoff magnetic flux density. Eight into 36 into 10 power 3 into E by M. So I can take it to like this 1.76 into 10 power 11. So this thing whole raised to half. Take the square root and divide it by B is 10 centimeter. So 0.01. 1 minus A square by B square.
Madam?
Yes.
Madam, B 10 centimeter, 10 into 10 power minus 2. Minus 2 means 0.1, no, madam.
Yes, yes. So why I did not write here is 5 and 10. Both the places there will be 10 power minus 2. So it automatically cancels, right?
Yes, ma'am.
So even if you don't write, if you want, you can write 0.05 by 0.01. It's the same as 5 by 10.
Madam, 0.01 or 0.1 only, no, madam. 10 centimeter means 0.1
Oh,
only, no.
sorry. Okay, that is 0.1. Sorry. So maybe you can let me know what you get. 17, some milli, milli. Should be milli, right?
Yes, ma'am. Milli, ma'am.
Okay, 17 milli Weber because it is magnetic flux density is Weber per meter square. Okay. Then next we have a question on TWT. So you see the structure of TWT just to give an idea of what is the structure here. So you have okay, let me go to the question first. In a TWT, the diameter of the helix is 2 centimeters. So what do you mean by diameter of the helix? This is the diameter, okay? This is the diameter of the helical structure. So, and the pitch is also given. So diameter is given as 2 centimeter and pitch is given as 2 millimeter. The phase velocity of the wave along the pitch, okay? Remember, this is in free space. Assume that this is in free space. And we need to find the phase velocity along this, along the pitch. Okay. So there is an equation for that. Vp is P into Z divided by square root of P square plus pi D the whole square, where P is the pitch and D is the diameter. pitch of the helix, diameter of the helix, from which you can calculate what is phase velocity. Is there any powers here? 95.44. 2 into 10 power minus 3 into 3 into 10 power. C is 3 into 10 power 8 meter per second. Square root of. Okay. So you have 9.54 into 10 power 6. Okay, let me just check it. I'm getting an answer 9.1 into 10 power 7 meter per second. Just please verify once again. Okay, the idea is clear, right? Maybe I'll check once again if there is any mistake. Okay, I think there was a mistake from my part. I haven't kept 10 power minus 2 here. Okay, that might be the mistake. So, yes, the right option is 9.55 into 10 power 6 meter per second. Okay. So that's all for today's session. Any questions, any doubts?
Hello, madam.
Hello.
Madam, which book you are following? Madam? Hello, madam.
Uh,
Hello.
Hello.
Madam, which book you are following, madam, for these problems?
Problems. Basically, it's the same reference textbook, but we look at the problems in different, like from different. What do you call it? If you search in microwave engineering questions, maybe I can give you some suggestions. You can just look in like Sand Foundry. There is some website, and then you have this assignment questions from different universities across the uh, uh, so they will have this questions and solutions. So maybe you can also refer those things. Just type in Google and you will see. So you have to type in microwave engineering which topic, assignment questions. So in fact you could get such things in there is one website. I'll just look at that one second.